Hello, happy Friday. Let's do some more related rights one more day. So if grain flows into a conical pile such that the height increases 2 feet per minute while the radius increases 3 feet per minute, at what rate is the volume increasing when the pile is 2 feet high and has a radius of 4? Let's draw our picture. So our cone, think of like making a pile. It's going to look like that. And we have a radius. And we have a height. Okay. So volume of a cone, 1/3 pi r squared h, again, a third of the volume of a cylinder, essentially. So now let's take the derivative. I'm going to look at this as product rule with 1/3 pi r squared being our f, and h being our g. dv dt, f prime, we're going to multiply the 2, so we have 2 times 1/3 pi r to the first power, just r, times dr dt, times our h. So that's our f prime times our g, plus derivative of h is 1, so really just 1 dh dt, which is just dh dt, times 1/3 pi r squared. So we had f prime g, and this is g prime f. So now let's plug things in. So dv dt is what we're trying to find. I'm going to combine 2 and 1/3 to be 2/3 pi. R is, let's see, radius is 4. dr dt is, let's see, 3. And then our h, is, well, 2 feet high, so our h is 2. Plus, now dh dt, rate of change of the height, rate of change of the height is 2 times 1/3 pi, and then r squared, well, our radius was 4, so this is times 4 squared. So now we really just simplify. So dv dt, let's see, 4 times 3 times 2 is 24, times 2 is 48. So we have 48/3. I'm going to leave it. 48/3 pi. I'm not going to simplify it to 16 yet. You could, though. Plus, 4 squared is 16, times 2 is 32 over 3. So 32 times 1/3, which is like 32/3 pi. 48 plus 32 is 80. So dv dt is 80 pi over 3. Since it's volume, it's cubic units, so it's feet cubed per minute. Now we have a plane. So our plane is flying horizontally. Oops, I'm gonna read, well, my plane's gonna be real bad, but here's a plane, here's the wings, and then maybe there's some windows. It looks more like a submarine with, like, I don't even know. But we're gonna say that's a plane, okay? It's flying horizontally at an altitude of 1 mile. Altitude is just height, right? So that's 1. It's going to be a right angle because if we're flying directly horizontally, we make a right angle with, your altitude. And then we can make a triangle, right? So this plane was flying directly above a radar station. So here's my radar station. It's like a house. There's a door. Okay, so we have a plane that's flying this way horizontally above a radar station. It passes right above it. And then we have a speed of 500. We want the rate at which the distance from the plane to the station. So the plane starts here and moves, then like the plane ends up, over here. I know my pictures are so good. So this is the distance from the plane to the radar station. And I call this A for altitude and this H for horizontal. So we need an equation. It's a right triangle. So let's do Pythagorean theorem. A squared plus B, sorry, it's not B though, right? It's actually A squared plus H squared, our A and our H, equals D squared. So then if we differentiate, we have 2A dA dt plus 2H dH dt equals 2D dd dt. So now let's look for what we know. So 2 is fine. A is 1. dA dt, well, it's actually a constant altitude, so dA dt is just 0 because that distance vertically is going to be 1 all the way across. Plus 2, we want our horizontal distance. We don't have it. Okay, so let's hold on that for now. dH dt, the rate of change of that distance right there is that speed of 500 miles per hour. So that's 500 equals 2. Well, our distance is 2 miles away because we're looking for when the plane and the station is 2 miles away from each other. So 2 times d, which is 2, dd dt, that's what we're trying to find. So this right here is what we're ultimately trying to find, the rate of change of the distance that the plane is away from the station. So it looks like we're going to have to figure out a way to find h, because we can only have one variable. Well, look, we have a triangle. We can use Pythagorean theorem. So we know that this A is 1, D is 2. We're trying to find h. We already know 1 squared plus h squared equals d squared from our initial equation, but now our distance is 2, so that's 2 squared. So 1 plus h squared equals 4. So h squared equals 3, and h is, oops, not h root 3, h equals the square root of 3. So then we can go back to our equation here. This goes to 0. So we have 2 root 3 times 500 equals 2 times 2, which is 4, times dd dt. So 2 times 500 is 1,000. We have 1,000 root 3 equals 4 dd dt. So to solve for dd dt, we can divide both sides by 4. 1,000 divided by 4 is 250. So we end up with 250 square root of 3. And dd dt equals 250 square root of 3, and our units were miles, and it's distance, so it's just miles per hour, mph, however you want to write that. For our final example, suppose an object is moving on a path described by y equals x squared. All right, I'll draw my parabola. So we have an object. Here's my object. It's moving around. We don't really know which direction where it is. So our equation is y equals x squared. We know at a particular time, say t equals 5, the x-coordinate is 6, and we measure the speed at which the x-coordinate is changing and find that dx dt is 3. At the same time, how fast is the y-coordinate changing? So this kind of sounds hard because it's like we haven't talked about parabolic paths. How does this work? But we have an equation, we have a picture. So now let's differentiate. We end up with dy dt equals 2x dx dt. And then from here, well, dy dt That's what we're trying to find, right? So we'll leave that. dy dt equals 2. Well, at t equals 5, I don't really care if t equals 5. We don't have any way to evaluate for t, but we know the x-coordinate was 6. So we have 2 times 6. And then dx dt, the speed at which the x-coordinate is changing, that was 3. So dx dt is 3. So dy dt equals 2 times 6 times 3, which is 12 times 3, which is 36. And we don't have any units for this one, and that's totally fine.